Welcome to the MOOCs course Transport Phenomena of Non-Newtonian Fluids. The title of today's lecture is Flow of Non-Newtonian Fluids through Packed Beds. Till now what we have seen different geometries where single phase flow taking place, like geometries like infinitely long cylinders or infinite parallel plates, inclined surfaces, concentric cylinders, etc. Those kind of geometries we have taken. Now in this lecture and then coming couple of lectures we will be taking a geometry where multiple particles are packed as a kind of bed, or maybe those particles under fluidized conditions, and then how to get the required frictional pressure drop for such kind of situations. So that is what we are going to see in this and in coming couple of lectures. Before going into the details of pressure drop calculations for the case of flow of a liquid, whether Newtonian or non-Newtonian, flowing through beds of particles, what we do, we will be having a kind of a list of applications where we can have such kind of applications, right. Examples of Newtonian and non-Newtonian fluids flowing through beds of particles. As chemical engineers, we must be aware that in any of the chemical industries or almost all chemical industries, we may be having a situations where we may be doing kind of filtration of slurries and then getting clear filtrate, etc. In general that is possible. So that may also be taken as a kind of a flow through bed of particles kind of thing. Like that sometimes polymer melts, slurries, sewage, sludge, etc. are also being filtrated using these packed beds or bed of particles. Then leaching of uranium from dilute slurry of ore in fluidized beds, another example. Then enhanced oil recovery where non-Newtonian polymer solutions are used to replace oil present in porous rocks. In general, what happens in petroleum rocks, a lot of oil is filled in the porous structure. So in the primary and secondary extraction process or recovery of the oil, so most of the oil is taken out from the oil rocks, right. But however, oil is very important energy resource. So then we cannot leave even a small amount or traces of oil in the rock. So then for that there is a tertiary method where that tertiary method which is also known as enhanced oil recovery method. So what we do in that such conditions where most of the oil is recovered, so only small amount is there that we cannot separate by using primary recovery method. So then we allow some liquids, sometimes Newtonian, but most of the times non-Newtonian polymer solutions are allowed to replace the oil that is present in the porous structure. So because these solutions are higher density compared to the density of the oil, that is crude oil that is present inside the rock. So then these polymer solutions that replaces that oil present in the rocks. So that is another examples. That is another example for the case where the flow of a non-Newtonian fluids flowing through beds of particles. So like that, if you keep on listing, there may be n number of applications, especially associated with the chemical engineering applications we may find. So having these many applications, obviously it becomes very much essential to find out the pressure drop, because wherever there is a flow, it becomes very essential to have a relation volumetric flow rate versus pressure drop, or equations for the pressure drop calculations or friction pressure drop, etc. are very much essential. So that is what we have been doing for so many geometries, right. So because that pressure drop is coming into the picture in velocity distribution or volumetric flow rate, etc., all those things. So that is indirectly we are having relations. If you have the velocity, you can get the other kind of thing. If you have the known fixed value of volumetric flow rate, how much pressure drop you need to apply, all those things we can calculate. So such kind of information is also required for the case of flow through packed beds or bed of particles, especially when the fluid is non-Newtonian, right. So pressure drop across such beds is very crucial for both design point of view as well as the operational tuning point of view of the associated equipment where these where any of the systems are having this bed of particles kind of system, right. So now we understand this bed of particles. So porous media is the one immediately that comes to the mind. So then it becomes very essential to understand what is this porous media. So though all these details, basic details we know from our UG level transport phenomena or fluid mechanics course. However, it is important to have a kind of a recapitulation of these basic concepts before going into the frictional pressure drop calculations for the flow through packed beds. Porous media is a solid structure with passage through which fluids can flow, right, and then it can be classified as consolidated and unconsolidated porous media, because this classification is one of the classification, not necessarily that this is the ultimate classification. There may be classification based on the other properties also, right. So, consolidated porous media are in general naturally occurring minerals such as sand, limestone, etc. So, these materials are often called as consolidated porous media. Whereas the unconsolidated porous media, in general, what we have like heat transfer taking place through a bed of particles, right, or mass transfer is taking place through bed of particles, or a catalytic reaction is taking place in a packed bed reactor where the bed is packed with catalyst or sand, etc. So, all that we do in general for our chemical engineering applications. So, such kind of beds or the porous media whatever are there, they are known as the unconsolidated porous media. These are packed beds of glass beads, catalyst particles, or rashing rings, etc. Those kind of materials are. Broken glasses, whatever different types of packing materials are available. So, these packing material are in general placed in a column. We have a column, in that column some portion of the column is packed with these kind of materials, so that to have a packed bed, and these packed beds are very much important in many of the transport phenomena problems, whether it is momentum transfer or mass transfer or heat transfer. Not only in the transport phenomena without reaction, but with reaction also there are many cases. So, such kind of self-made such kind of beds that we make for our applications point of view are known as the unconsolidated porous media, and then this possesses high permeability. So, obviously, this unconsolidated porous media whatever we have, they have higher permeability. If the permeability is higher, obviously resistance to the flow would be low. Then this packing can be ordered or random, but rarely we find completely random packing. However, some examples of completely random packing are cakes and breads. Cake material or bread material that breads we in general consume, we see. So, they are also having porous structures. So, then those whatever the porous structure is there, so that it's very random, and then interconnection between one pore to the other pore is very complex. So, how to characterize this porous material? Obviously, when you have a material, if you go into the engineering aspects, first one of the thing what we do, we characterize the material, we find the properties of the material, etc. So, now here in this case we have to characterize the media. So, how do we do that one? So, there are two possible ways are there. That depends on the scale at which are you using these porous media. If you are using these porous media at microscopic level, so then certain different characterizations are there. If you are using the same porous media at macroscopic level, like packed beds or fluid catalytic reactors, etc. So, then we have different characteristics, right. So, based on the scales at which we are using this porous media, this can be characterized macroscopic level as well as the microscopic level. The characterization at these two scales in general are complementary to each other. We cannot say one is superior to the other one, like that it is not possible to say. Sometimes both of them are very useful in general, or both the characterization may be used, but majority of the times they are characterized separately for different applications, right. So, they are complementary to each other and they are extensively used depending upon the objective, right. So, objective in the sense, let us say you have a column packed with activated charcoal, right, and then you wanted to separate out the color from a color solution. So, color solution you pass through that activated charcoal. So, then what happened, that activated charcoal will absorb the color that is present in the solution, and then almost like clear colorless solution you can get as a kind of filtrate from the other end. That is one application. So, now here the entire bed if you take, then you have to see the characteristics at the macroscopic level. But if you take individual particles, if you take one single particle and then see how much it is absorbing and all that, those calculations if you have to do, then you have to do the microscopic characteristics or this or characterization of such individual particles at microscopic level. Those things we have to see. So, at microscopic level, we in generally what we do, we find statistical description of pore size, pore volume, degree of interconnection, orientation of pores, surface area, like how many meters square per gram, etc. Those things that we get from BET equipment. So, all those things comes under microscopic level, even the isotherms etc. that we get. So, all these things comes under the microscopic level characterization of porous media. So, one example is like adsorption as just mentioned, right. Other level is the at macroscopic level. At macroscopic level, it is very essential to do proper characterization of the porous material, because most of the transport phenomena problem that exist in chemical engineering, we use this macroscopic level characterization. So, how do we do? Bulk parameters such as voidage, permeability, tortuosity, specific surface are used, right. So, those things are very essential, right. So, and these properties are averaged over scales much larger than the size of pores, okay. And these quantities are adequate for the process design where the fluid flow, heat and mass transfer are of interest, okay. So, these are the things that one has to be aware about a macroscopic level, and then these characteristics at macroscopic level are also reliable where the molecular dimensions are much smaller than the pore size, as I mentioned, like if you take individual char particle, it is a microscopic level, but if you take the same char particle but n number of particles you make as a bed, so then you can have a kind of a macroscopic level this thing. So, whether this macroscopic level is also reliable when the where the molecular dimensions are much smaller than the pore size as well. So, now this particular lecture what we are going to do, we are going to obtain frictional pressure drop for a packed bed at using the characteristics of the bed at macroscopic level. So, what are those characteristics? Just now we have mentioned the voidage, then specific surface, then permeability, then tortuosity. So, all these things are known to us. However, we have a kind of recapitulation. Let us say you have a vertical column, right, and there is a perforated plate at the bottom, and then we are packing this material with certain kind of particles, maybe glass beads or broken glasses or rashing rings, regular or irregular particles, whatever possible we are having. So, we are packing them, right, and then at the top again we have a perforated plate, okay, so that particles should not move out, and then this bed is compactly packed in order to that one. So, now the fluid is passing through here, some momentum transfer is taking place or heat transfer, mass transfer or whatever the reaction is taking place. So, let us not worry about those details. So, now what happens? So, voidages if you wanted to understand. So, then this height of the bed, let us say L, and then this cross section of the column is S naught, let us say. So, L multiplied by S naught would be the volume of the bed, right. Out of this volume of the bed, only epsilon fraction is available as a free space, so that these particles, these fluid particles to flow out. So, out of this total volume V is equals to L S naught, only some fraction is available, that is nothing but these interstitial spaces between the particle whatever is, so that is only available, and then particle goes away. How much is that one? That is we call voidage, that is the volume, free volume fraction out of the bed that is available for the fluid to flow through, right, that we call voidage epsilon, and then whatever the solid volume fraction is there, that we call it 1 minus epsilon. So, that is void fraction is nothing but free volume that is available for the fluid to flow through divided by total volume of the bed. The total volume is L multiplied by S naught, which is having two fractions. One is the volume fraction of the solid particles, another one is the void space or the free space of the volume fraction of this free space. Okay. So, that free space whatever is there, that we call it as voidage. And then these particles, like if you have only column, simple column, right, there is no packing. So, then it is possible that whatever the fluid element is coming, it may pass through straight forward without any deviations, right. So, but now here you have so many particles in between, so resistance is there from one particle to other particle. So, then fluid particle cannot go straight. So, the distance that any given fluid particle is traveling would be more than the L, because of these tortuous parts, and then that is characterized by the tortuosity. Right. Specific surface is the total surface area of the bed per unit volume. So, that is what another important factor. Permeability, how much volume, what is the velocity, at what velocity per unit volume of that bed it is passing through, those things we have to see. So, all these things are known to us, however, we have a kind of a recapitulation here. So, now we see one by one. So, voidage is epsilon, it is the fraction of the total volume available for the flow of fluids. It varies from nearly 0 to almost 1 depending on nature of porous media. If it is close to 1, that means the bed is very sparsely packed, and then lot of volume is available for the fluid to pass through. If it is close to 0, the bed is very compactly packed, that there is no or very little space available for the fluid element to pass through. So, then under such conditions, frictional pressure drop is going to be very high. Okay. So, either of the extremes are possible, but in general ceramic rocks, sandstones, etc., such kind of consolidated porous materials have the epsilon range 0.15 to 0.2, that is possible. So, but fibrous beds and then ring packings may have the epsilon value even up to 0.95. So, it is not like that only a certain range of epsilon in general we have, but it is possible close to 0, it is possible close to 1 as well, right. But however, most of the chemical engineering applications, epsilon whatever that we have would be varying between 0.4 to 0.6, or maybe in between 0.45 to 0.55, something like that. Specific surface, it is the surface area per unit volume of the bed, and then it is expressed S multiplied by 1 minus epsilon, right, because 1 minus epsilon is nothing but volume fraction of the particles. Now, we are getting the surface area per unit volume of the bed. So, then whatever the volume fraction of solids is there, that should be multiplied by the specific area of the particles, so that to get the specific surface of the entire bed. Okay. So, if you have this specific area of particles, that depends on the nature of the particles, which type of particles are you using for the packing. If it is spherical particles, then area of the particle is pi d square divided by volume of the particle, spherical particle is pi d cube by 6, 6 by d is the specific area of the particles, spherical particles. If you have a irregular particle, so then it will be different. There are different ways of getting these things also, that is also possible. We have seen in mechanical unit operations how to find out the specific area of particles if the packing is or the particles are irregular non-structured particles. Okay. So, we cannot go into all those details, you can go through those details. Then specific surface area range, it depends, again it is not necessary that it may be very small or very large. In general, for highly porous fibrous material, it may be order of 10 power 4, but for compact limestones it may be order of 10 power 6 meter square per meter cube. Then permeability, according to Darcy's law, for the flow of Newtonian fluids, the velocity of the fluid that is flowing through or the volumetric flow rate per area of the bed through which the fluid is flowing is proportional to the pressure gradient and inversely proportional to the viscosity. Whatever the proportionality constant K is there, that is known as the permeability. Okay. So, Q is volumetric flow rate of fluid, mu is viscosity of fluid flowing through the porous media, and then area A is the area of porous media normal to the flow, right, and then minus delta P by L is pressure gradient. Okay. So, then next is the K is the permeability of porous media. Units for the permeability is Darcy, and then it is defined as Porous material is said to have a permeability of 1 Darcy if a pressure gradient of 1 atmosphere per centimeter results in a flow of 1 meter cube per second of a fluid having a fluid viscosity 1 centipoise through an area of 1 centimeter square. So, that if you convert in meter square 1 Darcy, you will be getting 10 power minus 12 meter square. Lower the permeability indicates the higher is the resistance. Obviously, it is inversely proportional to the resistance, or it is otherwise. If the permeability is lower, then resistance would be high. If the permeability is higher, then resistance would be low for the flow to occur. Typical range of permeability is order of 10 power minus 11 meter square for fiber glasses, order of 10 power minus 14 meter square for silica powder and limestone, etc. Tortuosity, it is a measure of deviation of fluid elements from straight line path in the direction of overall flow, as I explained through the picture. If the column is not having any packing, so the fluid element that is entering and then leaving would be traveling the length of the L, which is the length of the column, but part of the column is packed with particles. So, then fluid element would be traveling more than the column length, right. So, or height of the column because of the tortuous path that has to pass through. Okay. It cannot go through straight because so many particles are hindering in between. And then obviously, this tortuosity should be depending on the voidage, particle size, shape and orientation of particles in relation to the flow direction. What do you mean by in relation to the flow directions? Let us say this is the column that you have, right. So, and then you are packing the material. If you have a needle like particles like this for packing, right. So, then this fluid element that is entering, that has to pass through different higher distance compared to the spherical particles, right. So, that is the reason the particle orientation of particles in relation to the flow direction is also essential. Let us say if the same bed, same needle like particles, if you packing like this parallel to the flow direction like this, the same needle like particles. So, then the distance that particle has to transfer, it will be still higher than the height of the column, but it will be less than the case where these particles are oriented in the normal direction like this. Okay. It becomes unit as the voidage approaches unity, and then for plate like particles, it is greater when they are oriented normal to the flow than when they are oriented packed parallel to the flow, okay, just as explained here. And it is not intrinsic characteristics of porous medium. Okay. Voidage, specific surface are the intrinsic characteristics of the packed bed, but tortuosity is not. So, now that was the recapitulation of characterization or characteristics, how to obtain the characteristics of a packed bed at macroscopic level through voidage, specific surface, tortuosity, permeability, etc. Those things we have seen. So, now what we do for the same cases, for the same packed bed, what we do, we try to obtain the pressure drop in flow through packed beds. Flow passage through beds of particles is very random and complex to have simple analytical solution for pressure drop. If you have a simple pipe, we already have done the analysis how to get the pressure drop, velocity profile, or volumetric flow rate versus pressure drop calculations, etc. All those things we have already seen. Now, we have particles, right. So, the packing is like this, so much of packing is there, right. Because of this packing, what happens? The flow is not uniform or not same from one location to other location, even. So, that is fully developed flow or like simple streamline flow or laminar flow kind of thing in the entire column is not possible. Let us say in the packing, if it is like this, so it may happen that in some portion it may be having, in this region maybe it may be having like laminar region or low velocity region, whereas in this region it may be having a very high velocity turbulent flow kind of thing. So, the flow is very complicated, you cannot generalize as a kind of laminar flow transition flow or turbulent flow, like that. Within the bed, certain region, one region you may be having streamline flow, another region you may not have streamline flow, you may be having turbulent flow, all that is possible. And then because these complications, now how do you generalize? The problem with this one, generalizing this one, how do you generalize in order to have a simple Q versus minus delta P relation, as we have done for the flow through simple pipe or infinite parallel plates or inclined surfaces or concentric cylinder, etc. That is not possible here because of this random and then complex packing that we are having in the bed, and then because of that packing the flow is very complicated. So, analytical solutions for pressure drop are not possible in general, but however we make some kind of assumptions or engineering simplifications in order to get certain analytical solution for these cases as well, but there may be some constant, those constants we may be fixing based on the experimental results. How to do all that we are going to do anyway. So, thus interstitial void space may be simplified as consisting of tortuous conduits of varying cross sections. So, what you do now, this bed is there, it is having certain void space. So, right, at certain given minus delta P values it may be having certain velocity. So, now what you do, you can have a different conduits are of different size like this, right. So, that and then you join them together, so that whatever the characteristics, like here that we are having for the packed bed, especially in terms of the void edges and then specific surface, etc. So, the same you make a kind of n number of conduits, so that those n number of conduits when joined together you will be having a kind of void edge and specific surface same as the initial bed. So, that way we do, and then we make a simplification to get the required pressure drop versus volumetric flow rate relations. So, what we do, thus interstitial void space may be simplified as consisting of tortuous conduits of varying cross sections, but having a constant average area for flow, which is same as the case of real packed bed. With this approximation of bed voidage, flow in porous media is equivalent to that in non-circular conduit offering same resistance to flow as a bed of particles offering. So, generally flow passages in a bed of particles are oriented or interconnected in an irregular manner, that we know. Thus, elementary capillary models cannot account for real life complex void space of the beds in general. So, however, analogy between flow through circular tube and through channels in a bed of particles provides basis for deriving general flow rate versus pressure drop equations. So, that we are going to do now here. How do we do? So, now this is the case real life packed bed, where the bed is packed with spherical particles like this. In real life problem, we have a packed bed which is packed with spherical particles like this. Okay. So, the diameter of these particles is d, the height of the packing is L, the cross section area of the column or the bed through which the fluid is flowing is A, and then the fluid is flowing at volumetric flow rate Q. So, which may be corresponding to some average velocity V naught Q by A. So, now what we do, we replicate this system to have a number of conduits, non-circular conduits like this. Okay. So, that here also we get average velocity V naught is equals to Q by A, same as packed bed. Pressure drop would also be same thing, and then this L is going to be LE, because L is the fixed one, but fluid particles we have to take with respect to the fluid particle. Fluid particle may be travelling more than the L value, as I mentioned, because of the tortuosity. So, that is the reason we have LE here, and then whatever the void space because of these non-circular conduits that we are having, that you take a D effective, right. So, because for this case, let us say if these columns conduits, if you have a kind of circular pipe, n number of circular pipe. So, then if the flow is, let us say in this one, if you have the streamline flow, in the packed bed if you have streamline flow. So, such kind of streamline flow if you have using a capillary or if having a circular tube. So, then for circular tube streamline flow is taking place. So, then we know the Hagen-Poiseuille equation, right. So, that Hagen-Poiseuille equation now we use here whatever the Hagen-Poiseuille equation is there, and then whatever the L, D or V etc. that are there in Hagen-Poiseuille equation, they will be replaced by the realistic true L, D, V of the packed bed. So, that kind of analysis we do, right. Hagen-Poiseuille equation for a flow of Newtonian fluid through circular pipes is nothing but minus delta P by L is equals to 32 mu V by d square. This is what we know. The same thing for the power law fluids we have derived in one of the previous lecture week 3 or 4. This is what we have derived. In this equation if you substitute n is equals to 1, you get this Newtonian case, right. So, in this case what you do now, in place of D you find out D equivalent, right, which gives the same average velocity like in packed bed, and then this V you replace by the velocity that is there in the interstitial spaces. In the interstitial spaces, what is the average velocity? Thus, let us say Vi that we call interstitial spaces, that you replace, and then this L you replace by effective length, that is the particle is flowing through, and then you substitute here. So, then you get required pressure drop relation for the streamline flow in packed bed. That is what you can get by this analysis or by this analogy between packed beds and then a number of non-circular conduits or circular conduits, whatever you take. Okay. So, that is what we are going to do. So, now the question is that what is this Vi, what is this D equivalent, what is this Le? So, those things only we have to find out, and then after that the problem is simply mathematical. For flow through a non-circular duct, above equation may be rearranged as this one. Okay. The previous equation whatever V is equals to d square by 32 mu minus delta P by L was there. This is for the circular column tubes kind of thing, for Hagen-Poiseuille equation. But the same equation if you derive for non-circular conduits, you get this one. Here dH is nothing but hydraulic radius, and then this constant K naught depends on the shape, okay. So, dH is hydraulic mean diameter, which is nothing but 4 multiplied by pore volume per surface area of particles, and then K naught constant, which depends only on shape of the cross section, right. Which shape you are taking? If you are taking circular cross section, then K naught should be 2, so that here you get 32 like this case. Okay. So, that is for circular tube of diameter d is equals to dH, K naught should be 2. Likewise, for flow between two plates separated by a distance 2h, dH should be 4h and K naught should be 3. So, this flow between two plates that already we have derived in a couple of lectures before. So, then there also we have the average velocity expressions, that equation you rearrange in this kind of form. So, then you can get that when you rearrange that equation in the form of this one. So, then you get K naught is equals to 3. Okay. Now, that same equation 5 for non-circular conduits we are rearranging. How are we rearranging? We are writing minus delta P by L dH by 4, one side we are writing, other side whatever the remaining terms are writing, we are writing. Okay. So, now here what we have, minus delta P by L d by 4 is nothing but what? It is nothing but shear stress, right. So, now this shear stress is at the wall of flow passage, right, at the wall of the flow passage, that is along the particles whatever I say. So, that is changing from along the from one particle to other particle, but we are taking average shear stress at wall of flow passage. It is not at the wall, right, wall of the flow passage. It is not at the wall of the column, but at the flow passage. That is, you have these particles like the packing like this. So, now when the fluid element is moving, there is some shear stress here, some shear stress along this, some shear stress along this, some shear stress along this. So, all that shear stress along the fluid passage areas whatever is there, that is average, that is minus delta P by L dH by 4. It is similar to whatever the tau Rz that we got minus delta P by L is minus delta P by L R by 2 for the case of circular conduit. So, analogy to that one, this we can write as a average wall shear stress, right. And then right hand side whatever is there. So, mu is what? Mu is viscosity, and then shear stress is equals to viscosity multiplied by the shear rate. So, then whatever the parenthesis term here 4 k naught V by dH should be what? It should be shear rate. It should be the true shear rate. 4 k naught V by dH is true shear rate for the case of Newtonian fluids, but it is a nominal shear rate for the case of time independent non-Newtonian fluids, generalized Newtonian fluids, that we know already. Okay. This is also at the wall of flow passages, not at the wall of the column. Okay. So, if you designate this symbol for average quantities, so this equation number 6, how we can write? Average tau W is nothing but dH by 4 minus delta P by L, and then average nominal shear rate is nothing but 4 k naught V by dH. Okay. So, these two equations we are going to use later on when we do the frictional pressure drop calculations. So, now this equation can be used to obtain expression for pressure drop in streamline flow of generalized Newtonian fluids through beds of particles by replacing V by interstitial or the pore velocity or mean velocity in pores or interstitial spaces Vi, and then replacing L by average length of tortuous path Le, and Le is nothing but T multiplied by L, T is nothing but the tortuosity factor. Okay. So, interstitial velocity Vi is related to the superficial velocity V naught. How it is? It is related like Vi is equals to V naught by epsilon. How it is, that we see now. For a cube of side L, the volume of voids is epsilon L cube voids, or a cube, if you have a particle is a cubical shape, let us say the particle that you are taking, it is a cubical shape, then its volume is L cube if the side of cube is L. So, out of these n number of cubes are there, so then void space is the volume of the voids is the epsilon multiplied by L cube, that we understand. Then mean cross section area is free mean volume divided by the height, that is epsilon L cube by L. So, that is epsilon L square, right. Then the volumetric flow rate through the cube is given by V naught L square. Through the cube, whatever the volumetric flow rate is, that is nothing but whatever the average velocity V naught multiplied by the area, that is L square. Okay. So, now average interstitial velocity Vi should be obtained by V naught, this volumetric flow rate divided by the mean cross section area, that is V naught L square by epsilon L square. So, that is V naught by epsilon is nothing but Vi. Okay. So, this is how we get this interstitial velocity or the pore velocity or the average velocity in the pores. Now, if you consider tortuosity factor also, so this V naught by epsilon should be multiplied by T. Some books it is multiplied, some books it is not multiplied, because there are so many constants are there, all together they are clubbed at the end when you have the final frictional pressure drop relation, and then compared with the experimental results, and then this combination of whatever n number of constants are there replaced by 1 or 2 constants alpha or beta, like that. Okay. Those things we are going to see. So, hydraulic mean diameter in terms of packing characteristics we have to find out. For a bed of uniform spheres of diameter d, it can be like dH is equals to 4 multiplied by 4 area divided by the wetted parameter. So, flow area is nothing but the volume of flow channels, okay, that is available, and then wetted perimeter is nothing but the surface area of particles. So, now what we do? We divide numerator and denominator by total volume of the bed. So, that volume of flow channels divided by the volume of bed we can write as epsilon void fraction epsilon, and then surface area of packing divided by the volume of bed, we can write it as specific surface SB. SB for spherical particles, we know S multiplied by 1 minus epsilon, and then S for spherical particle is 6 by d. So, SB is nothing but 6 by d multiplied by 1 minus epsilon, right. So, now dH is here 4 epsilon divided by SB is 6 by d 1 minus epsilon. When you do simplification, you get dH is equals to 2 by 3 d epsilon by 1 minus epsilon. Okay. So, now LE effective length we already got as T multiplied by L, that is height of the packing. VI interstitial velocity we got it as V naught epsilon multiplied by T, and then dH we got it as 2 by 3 d epsilon by 1 minus epsilon. So, now these 3 quantities we are going to substitute in tau W and then gamma dot Wn average values, right. So, when you substitute here, tau W is dH by 4 minus delta P by L, dH you substitute from equation number 13 here, and then you simplify. So, average tau W you get this one. Now, similarly, average gamma dot Wn average nominal shear rate is this one, 4 K naught Vi by dH. Vi you substitute V naught by epsilon T, dH you substitute 2 by 3 d epsilon by 1 minus epsilon, and then simplify. So, then you get this one, right. So, but still here if you wanted to know the tau W, you need to know the pressure drop, right, a priori, but we are doing all these calculations in order to get that pressure drop or frictional pressure drop in terms of F, right. So, these equations are not final, directly we cannot use, because though all other terms are like epsilon, d, etc. are available from the experimental results, right. So, you cannot a priori cannot calculate the shear stress or shear rate using these expressions, because this minus delta P by L is not available. So, for that reason what we do further simplification and then obtain frictional pressure drop expression rather than pressure drop. So, for generalized non-Newtonian fluids, Kemlowski have reported that the shear stress at wall of pore or capillary is related to corresponding nominal shear rate at wall by a power law type of relation, and then that relation is given by this one. Tau W is equals to m prime gamma dot Wn whole power n prime, and these m prime and then n prime are not the rheological parameter of the fluid. They are not the rheological parameter of the fluid, but rather they are obtained by the pressure drop versus volumetric information from the experimental results. Okay. So, from the experimental results what people found, this n prime is equals to n, but m prime is m multiplied by 3n plus 1 by 4n whole power n. So, this m and n without primes, they are the rheological parameters of the fluid, whereas n prime and then m prime are the characteristic parameter that are obtained from the packed bed by doing experiments and then getting the results volumetric flow rate versus pressure drop. So, now what we do? We define the friction factor. Friction factor, how we define? F is equals to tau W by of rho V square. So, tau W is minus delta P by L d by 4 and then divided by of rho V square. This is what we have. So, then from here this same thing, if you write minus delta P by rho, you can write it as 2 F L V square by d. This is what you can have. So, that equation is written here, right. So, now in place of L we have to write LE, in place of V we have to write VI, in place of D we have to write DH for the packed bed, and then corresponding equations that we have already derived in previous slide we substitute here. So, then you get expression for F as this one, F is equals to minus delta P by rho DH by 2 LE VI square. So, this is nothing but your frictional pressure drop. This is nothing but the frictional pressure drop expression. So, now this 1 by 3 T constant, that is we are not taking, because we are writing as a kind of generalized expression. So, those constants are taken care by the final friction factor in terms of Reynolds number that we do. So, this frictional pressure drop we can get from this expression, okay, if you know the friction factor. If you know the friction factor minus delta P by L, you can find out. Okay. So, how to find out the friction factor for a packed bed, that we do. So, tau W we have this one, gamma dot W n we have this one already from equation number 14 and 15 we have derived. So, F we are having this expression. So, in place of minus delta P by L, what you write, tau W multiplied by 6 1 minus epsilon T by d epsilon from equation number 14, and do the simplification. Before doing the simplification, now this tau W is nothing but it is equals to m prime gamma dot W n whole power n prime, right. So, that we write now here. So, m in place of tau W we write m prime gamma dot W n whole power n prime. This is what we write in place of tau W. Then remaining terms are as it is. Next step, in place of m prime we write m multiplied by 3n plus 1 by 4n whole power n, right, and then in place of gamma dot W n we write whatever 6 k naught T 1 minus epsilon by epsilon square V naught by d, this is what we write, and then whole power n prime is n, right. So, this is coming from equation number 15 here, okay, in place of gamma dot W n. So, now after doing this one, if you simplify, so this is the equation that you get. So, now here in this equation you do not have any unknown kind of thing, right. Usually this k naught T epsilon for a given packed bed, they are known from the experimental conditions. Average velocity, how much average velocity you wanted to have through the bed, so all those things are known. Fluid rheology is also known a priori. So, then friction factor you can calculate using these relations. So, if the friction factor is there, so pressure drop you can find out. Okay. So, the same equation rewritten here. So, now this equation what are we trying to do? We are putting these constants 6 k naught T power n 6 T, these are the constants. So, these constants we are keeping in the numerator, and rest all the terms we are bringing to the denominator. Now, k naught in general for most of the case can be taken as on average 2.5, and then T in general for most of the case is square root of 2. So, if you substitute k naught T here in place of 6 k naught T, you will get 15 square root of 2, power n is as it is, and then 6 square root of 2, right. So, now next step what we are doing, we are just multiplying this term here. What we do, 15 square root of 2 whole power 1 minus n, we are doing multiplying numerator, and then with the same quantity we are multiplying the denominator as well. So, that in the numerator we have only 15 square root of 2, and the denominator whatever is there 15 square root of 2, that is 15 square root of 2 divided by epsilon square whole power 1 minus n we can write, and rest all the terms are as it is. So, this 15 square root of 2, 6 square root of 2 is nothing but 180, and then divided by all these things as it is. So, this is in the form 180 by Re, right. All this is nothing but Reynolds number for a power law fluid flowing through a packed bed, like REMR that we have defined for a case of power law fluid flowing through a circular pipe. Now, same power law fluid is flowing through packed bed, then Re is defined by this whatever the quantity in the parenthesis, that is rewritten here. Okay. So, for the streamline flow of a power law fluid flowing through a packed bed, the friction factor F is 180 by Re star, that is what we got. Okay. So, for Bingham plastic fluids also we can do similar analysis, but not much literature is available. But if you follow the similar analysis for the Bingham plastic fluids we found this expression. This is also we have done in the week number 3 or 4 sometimes previously. So, this is what we have, we adopted it here. So, this equation we can write like this. V average, right. Next here phi is nothing but tau naught B by tau W, that we have been discussing whenever we are having these viscoplastic fluids, right. So, now you apply the similar analysis like you have done for the power law case, or what you do, you rewrite this equation like minus delta P by L d by 4 one side, and then remaining terms other sides if you take, you get these things, or you can do 8 V by D multiplied by whatever these remaining constants. So, then this is what you are getting, this expression you get here. 8 V by D is nothing but nominal shear rate, that is equals to tau W divided by mu B multiplied by this factor whatever is there. It is just a rearrangement of this equation. Simply you write 8 V by D one side, and then all other terms you keep other side. So, 8 V by D is nothing but the nominal shear rate for generalized Newtonian fluids, and then right side wherever minus delta P by L d by 4 was there, that you write tau W, and then remaining terms are as it is. So, like that if you do and then follow the same analysis by replacing V by Vi and D by Dh and L by Le, then do the similar calculation what we have done till now for the case of power law fluid, then you get F is equals to 180 by Reb F phi as a kind of friction factor for a Bingham plastic fluid flowing through packed beds, where Reb is nothing but rho V naught D divided by mu B 1 minus epsilon, and NFB is nothing but that phi function 1 minus 4 by 3 phi plus 1 by 3 phi power 4. Okay. Phi is nothing but tau naught B by tau W as we already seen. So, that is all about the streamlined flow of a power law or Bingham plastic fluid flowing through packed bed. What if the flow is transition or turbulent region? If it is in transition or turbulent region, so then what should we do? Similar analysis one can do, or from the experimental analysis you can take some empirical correlation, that is possible, right. However, for non-Newtonian fluids usually apparent viscosity is higher, so then in general you do not get very large Reynolds number flows. Okay. Also, there is no clear cut value of Reynolds number for flow transition in the case of packed bed, even for the Newtonian case. So, same is valid for non-Newtonian case. So, experimental observation have found that this critical Reynolds number where the flow is changing from streamline to transition or turbulent flow, that increases with decreasing the power law index. It is completely experimental observation. And then other factors due to wide range of pore sizes, flow in some pores can be laminar and in some other pores can be turbulent, these kind of other factors are also there as I already mentioned. So, however, the cutoff Reynolds number from streamline to transition flow is taken between 5 to 10 value of Re star for many of the applications, and then people found approximation is good for many of the engineering design calculations. Okay. So, what we see a few literatures. So, Mishra et al. And Bray et al. Proposed following empirical method for estimating the effective viscosity for a fluid flowing through packed beds. That viscosity is given by this one. This is for the case of power law fluids. And now using this one they have defined the Reynolds number Re prime. So, like rho V naught D by mu 1 minus epsilon is the Reynolds number for a Newtonian fluid flowing through packed bed. So, in place of mu we have the mu effective. So, now you substitute mu effective here and then get the Re prime for the case of power law fluids flowing through packed beds. Further, these researchers assume the viscous and inertial components of the pressure drop are additive, and then they proposed following correlation between friction factor and modified Reynolds number like this. This is for the entire range, not only for the streamline, but also it is covered transition range also, right. This is the this form they proposed, and they found this alpha is equals to 150 and then beta is equals to 1.75 as per the experimental results of Mishra et al. Their experimental conditions are very narrow, like n is 0.721 and then Re prime 0.01 to 1000 only. However, epsilon range they have taken very wide, 0.37 to 0.95, right. Now, with these values of alpha and beta, whatever the f is equals to alpha by Re plus beta is there, that is coinciding with the Newtonian results, because for the Newtonian results Ergun's equation we know that f is equals to 150 by Re plus 1.75. So, same constant they also got here, only thing that Reynolds number is modified Reynolds number they have, and then that modified Reynolds number is equals to the Reynolds number case of the Newtonian case if the fluid is Newtonian, right. But however, Bray et al. Also performed several similar kind of experiments, and they proposed alpha should be 160 and then beta can be 1.75, same like Mishra et al. Only alpha is changing. However, their range of conditions are also very different, right. So, they have taken wide range of n values, but voidage is very narrow, and then Reynolds number is slightly higher, up to 1700 they have taken. Okay. So, like that many correlations are there with slight different constants etc., right. However, one has to be careful using which correlation. So, for that Reynolds number we have to find out. So, based on the more literature and new data after the works of Mishra et al. And then Bray et al., people found when epsilon is less than 0.41 and then when Re star is less than 100, it is better to use f is equals to 150 by Re star plus 1.75, whereas if Re star is greater than 100 and then epsilon is greater than 0.41, it is better to use f is equals to 150 by Re prime plus 1.75. The constants are same, but only this Reynolds number, different definitions of Reynolds numbers we have to use depending on the values of epsilon and then Re star. Okay. So, some other variants of capillary models are also available in the literature. At low Reynolds number, pressure drop varies proportional to V naught power n. So, from the momentum equation itself we can understand. So, the pressure drop, the viscous terms are having power n in the case of power law fluids, whereas the inertial terms, that is at the high Reynolds number case, pressure drop varies as power of V naught square, because inertial terms whatever are there, they are having V square terms. So, this is standard basic understanding from the momentum equations also we can get, right. Sabiri and committee assumed these contributions low and then high Reynolds number cases are additive and then proposed the following correlation. The proposed F4 is equals to 16 by Re4 plus 0.194. The constants are different, the altogether Reynolds number definition is different, and then F definition is also very different according to them. How are they different? That we are going to see, but they are defined based on the interstitial or pore velocity. So, REPL that we know, we are now trying to define what is that F4 and RE4, right. For that what we do, we take the REPL definition that we have rho V average 2 power n minus n d power n divided by 8 power n minus 1 m 3n plus 1 by 4 n whole power n. This is what we have seen REMR or REPL in week number 3 or week number 4 when we are studying flow through pipes. So, now in these equations in place of D we write DH, that is 4 epsilon by S 1 minus epsilon, and then V average we write V naught by epsilon T, and then do the simplification then if you do this replacement, whatever the REPL is there, that would be RE4, and then after doing certain simplification, this is what you get, very complicated expression. Similarly, F also we have minus delta P by rho is equals to 2 FL V square by D. So, there also in place of L you write LE, in place of V you write VI, in place of D you write DH, and then do the simplification. Then whatever the F is there, that would be F4, right. So, that expression is given by this one. After some simplification you can get this. So, now before winding up today's class, we take an example problem, right. So, that to understand which expression should we use, especially when we have a flow of a non-Newtonian power law fluid flowing through packed bed. Okay. A polymer solution of density 1008 kg per meter cube obeying shear thinning power law model with m is equals to 3.7 Pascal second power n and n is equals to 0.5 is flowing at 10 power minus 3 meter cube per second through a 50 mm diameter column with 1.5 mm diameter lead shot. So, small d is 1.5 mm, okay. Capital D is 50 mm. Okay. N and m values are given, q is given as 10 power minus 3 meter cube per second, rho is given, average voidage also epsilon is given as 0.39. Estimate the frictional pressure drop under these conditions. So, what we have to do? We have to find out the Reynolds number, as we have seen Re star we have to find out. If Re star is less than 100, because epsilon is less than 0.39, if Re star is also less than 100, then we can use F is equals to 150 by Re star plus 1.75 expression. If Re star comes out to be more than 100, then we have to use F is equals to 150 by Re prime plus 1.75. So, then again Re prime we have to find out. So, in order to select the equation, we have to first calculate the Re star. So, if you want to calculate Re star, you need V naught, that is you can get by Q by pi d square by 4, Q is given, D is given, column diameter is given. So, V naught you get 0.51 meter per second. Re star expression is this one. So, now here in this equation rho, V naught, D, N, M, epsilon everything is known. So, when you substitute you get 52. So, it is less than 100. So, then you can use F is equals to 150 by Re star plus 1.75, this equation you can use. So, then you get 4.63 as friction factor for this fluid flowing through the packed bed of given characteristics. So, then if you have this one, pressure drop you can find it out as minus delta P by L is equals to F rho V naught square D multiplied by 1 minus epsilon, epsilon cube. Now, here F you substitute, rho, V naught, D, epsilon etc. all are known substitutes. So, then you get 8.3 megapascals per meter. The references for today's lecture, the entire lecture is prepared from this reference book by Chabra and Richardson. Other references are provided here. Thank you.